Hello class, today we're going to be talking about applications of exponential and logarithmic functions. And so the notes on page 123 are very important, and we're going to go through some examples on page 122. So please print those out before you really start watching the video. So as you remember, an exponential function is a growth function, i.e. always increasing, if the base of the exponent is a number greater than 1. And as we can see here, this is what an exponential growth function looks like. And the growth factor is called is what b is called, the base is called. And if base is greater than 1, then you're going to have an exponential growth. But today we're going to be talking about another way to write an exponential growth function. And this is in terms of something that occurs in nature. So the natural growth function, in other words, is always growing, and this is something that seems to occur a lot in nature, looks of the function a naught, which is called the originating value, i.e. the starting value when time is 0, or the y-intercept, and e is the base, and we know that e is around 2.7, so we know that it's greater than 1, so that's why it's a growth function. And then we have another variable, k, and if k is greater than 0, and it's still constant, but if k is greater than 0, then that's what makes this a growth constant. And let's take a look at an example of a graph. So I've let in this problem k be a number between -10 and 10, and k can be a negative or a positive number. But let's look what happens when k is a positive number. As you can see, the graph looks to be exponential growth. And the more positive k is, the wider, the growth function it is. But if we look at what happens when I make k negative, then it becomes an exponentially decay function because it's always decreasing. And that's something we have to realize. So if k is positive, you can always have an exponential growth function. So let's get rid of this graph and just look at this one. In this case, the originating value is 4. And if we look at here, it crosses the y-axis at 4. If I change this value to 6, then it crosses the y-axis at 6. So this first number is, this first constant, a naught, is called the originating value, and it's where the graph crosses the y-axis because the t value or input value is 0. E is the base, and as we can see here, the exponent is 3 times t, so our k is 3 in this case. So back to the notes, we have an example of an uninhibited growth of cells function, which is an exponential function. So if I want to know how many cells I have in a culture after time t is passed, then that can be explained or described by this function, where n naught is the initial number of cells, e of course is the base, k is a positive constant that represents the growth rate of cells. So some cells grow faster than the other cells, so that's why their k value may be higher. And t represents the time. So different types of cells have different constants of growth, and that's what will determine what k is. But not only is this an example of growth of cells, we can also use this function to represent the population growth. So let's take a look over here at page 122. Oops. In the last 12 years, an initial population of 38 buffalo in a state park grew by about 7% per year. So what does that mean? Well, for our function, instead of our base being e, we know it's going to be a positive number because you're growing. So that means when we want to write an exponential growth model, given the number of buffalo after t years, what will it look like? Well, what we're going to do is, let's take a look. What's the initial amount? The initial amount, well, how many do you start off with? They tell you is 38 buffalo. And then the percent increase is 0.07 because 7% is the same as 0.07. So the exponential growth model, to make sure, since it's growth, we know that the base is greater than 1, looks like a, which is the original value, 1 plus the rate raised to the t power, and we have something that looks like this. And if I want to figure out how many buffalo there will be after 7 years, I just plug t in for 7 and I'll get my answer. So let's see. I plug that into the calculator and I calculate it, and the answer will be around 61 buffalo. Okay? If they want me to graph this, all I have to do is do graph number 1, which is the starting value, which we said is 38 buffalo, or original value, which is 38, and then pick another point. So let t be 1, and I know that when I plug t in for 1, I'm going to get around 41. So then we draw a curve that goes through 0, 38, which is around here, and 141, and it's going to look something like this, exponential growth. Okay? And if we want to estimate after 7 years, where will it be, all we have to do is see where, when t is 7, where this graph will intersect. Okay? And we can also do the same thing for in rate of inflation. So here we have a new television costs $1,200. The value of the television decreases by 21% each year. Now we're going to write an exponential decay problem. Now let's go back to our notes to see what exponential decay means. Exponential decay is of this form, a times b to the x, where in this case it's the same as the original growth function, but instead of b being greater than 1, now b is a number between 0 and 1. And in this case, the decay rate is the decay factor is what b is when it's less than 1. Well, if we want to look at decay in nature, there are several examples, but it still looks like the same function as exponential growth, except that in this case, k has to be less than 0. So an example of that in nature is the decay amount of radioactive material present at a time t. It looks very similar to a not e raised to the kt, where a is the initial number of radioactive material, but k is a negative number. We can also see something like that in Newton's law of cooling. It looks to be an exponential function, but a transformation of one. But here, k has to be a negative number. Okay, so let's take a look at an example of decay where the base is a number that's less than 0. Or we can represent this where e raised to the k, where k is a negative number. So let's go back down to number 3. Since we're talking about the value decreases by 21% each year, we can write a model to figure out how much the value of the TV will be after t years. So what's the initial amount? Well, it initially costs $1,200, so that is our A, and the percent decrease is 0.21, 21%. But instead of it growing by 21%, it decreases by 21%. So let's make sure that the base is negative. So we're going to write an exponential decay function where we replace A with 1,200 and R with 0.21, and we get something that looks like this. Well, 1 minus 0.21, well, 1 minus 21 is roughly 0.79. So I can rewrite this function as 1,200 times 0.79 to the t. And as you can see, the base value is -1, and that's where we have our answer. And if I want to figure out after 2 years how much the TV costs, I replace t with 2, and I get my and I can plug that in and get an answer of around $750. Okay? So in order to make, instead of making the base value a number between 0 and 1, we've kind of determined that by changing k in this problem. And if k is negative, then that means you're going to have an exponential decay problem. And Newton's law of cooling is an example of that, as long as k is a negative number. So in order to find a function, an exponential growth or decay function, we need to definitely figure out what k is and what the originating value is. And once we do that, we can plug it in. Now we have an equation that represents our function. Now we can also represent something as far as a logistical growth. It's still growth, but it's growing slowly. So what we do is we have something that looks like this. If it's a logistical growth, it grows very slowly in comparison to exponential growth, which grows very quickly. But here we have an example where we have a lot of different constants. C is a constant, the originating value is a constant, and B, or sometimes we use as K, is another constant. As long as C is greater than 0 and B is greater than 0, it's going to be growth. If B is greater than 0, if B is less than 0, it is decay. And so C represents the carrying capacity because it's actually going to be a limit. So it's going to look something like this if it's growth, and it's going to look something like this if it's decay. And that value that where it reaches the max, like it's a horizontal asymptote, is C, no matter if it's exponential growth or decay. Okay, and the point where it changes direction of the curve is called the inflection point, and that inflection point is at the y value of half of the carrying capacity. And so what you're going to do is set up equations that represent that. So it's very important that you identify what K is and what the other constants are, and then you'll come up with an equation.